Thank you for joining me. I'm Maya Lesov. Today we're speaking with Dr. Robert Ely, who is an assistant professor of mathematics at the University of Idaho. Dr. Ely's research focuses on the way students think about the infinite and the infinitesimal in math. He's also one of the leading investigators on a team working on a $5 million National Science Foundation grant designed to support math teachers who promote mathematical reasoning and generalization in elementary and middle school classrooms in Idaho and Washington. Welcome, Dr. Ely. Thank you for joining me.
Thank you. I'm glad to be here.
So you are clearly a math educator yourself, and your research focuses on math education and comprehension in students. So tell me why you're interested in that topic and why maybe the field needs your attention.
Oh, well.
Or someone's attention.
I mean, it's a huge problem to figure out how we get people who aren't perhaps naturally interested in mathematics, or people who don't view themselves as being tremendously gifted in mathematics to learn this stuff. Like, how do we get people who are good teachers? And I think that this is one of the most interesting problems that we can face for researchers, is like, not just do we understand mathematics ourselves, but do we understand all of the things that go into mathematics, and can we organize those things that go into the mathematical content ideas so that students learn them gradually. I think it's really compelling to try to problem solve what it means for someone to learn math, not just to solve math problems themselves. I've always been interested in this ever since I was in college, and I was reflecting on my own math teachers, and I was able to explain certain things to my friends that the teachers couldn't, and it wasn't because they were poor teachers, it was because they were so far from those ideas, from when they were learning those ideas themselves, that they didn't understand all of the little pieces of knowledge that they already had in their heads that went into those things. So that's what got me excited about it.
Do you have to work at remembering what it was like for you as a student all the time?
Yes, absolutely. That is a huge part of this, to be able to say, okay, when you're a student, here's something that you think that isn't exactly right or isn't totally generalizable, and here's what you need to think, and here are the steps in between that you need to, like the realizations that you need to come to in between. That's stuff that I have to have written down, I have to look up, I have to have sort of notes for. That's what a lot of the research in math education is about, is developing like what those pieces of knowledge are. And it's extremely hard for people who know math very well because it's all just in a little package for them. They don't need to know that there are two different kinds of division, not just one, and that students don't see those two kinds of division as the same thing, for example.
So you struggle with that as well, or have to remind yourself?
Oh yeah, and in calculus class,
Yeah.
I have that same issue. People are puzzled by something and I don't realize, oh, there's a thing there that they don't totally understand. And I didn't even realize that that was something that you couldn't understand immediately, that you needed some other piece of support in there for.
What kind of response do you receive from students about your teaching style?
I don't know exactly how I would think about my teaching style. I think students tend to like it when people, like, one thing that I like to do a lot is teach using historical examples, and that's something that students tend to like a lot more. They like to see the human side of mathematics and know some of the stories of how these ideas developed, instead of just having those ideas delivered wholesale to them. So I think I've gotten a lot of students who like that, and who say, yeah, please give me more of that. Tell me more about where these ideas come from, instead of just the ideas themselves. That might be something that's part of my style.
Well, let's talk a little bit about why math might be puzzling to students. In my experience through school and throughout life, I've heard people say, well, it feels like people just invented it, and you go to school and they say, this is the formula, so just use it, and it's enigmatic for that reason. So can you answer the question of whether we invented math?
Oh, I mean, of course, that's extremely deep. This is a question that in my history of math class we deal with a lot, because there are different people who have, throughout the ages, had different stances on whether math is discovered, or whether it's invented, or whether it's some combination of the two. I think it is invented. I think that's really the right way to think of it. But it's invented for a reason. And those reasons are ones that all of us can understand. So it's not invented in the same way that a painting is invented, where it really just comes out of the mind of this one person, and they're trying to portray something that they are thinking and feeling that maybe the audience doesn't understand. It's invented to solve a problem or to address a situation that is something that all of us could see, and if we looked at those stable patterns and realities in our experience, we would see those same stabilities. Because we're the same kind of people. We have 2 legs and 2 arms like everyone else. We count the same way that everyone else. There aren't fundamental deep differences between the way one person sees discrete objects in the world and the way another person sees discrete objects in the world. So the idea of the number 3, it's an idea that we learn. It was invented by someone, but it's invented in a way that can encapsulate and describe the reality that all of us experience, I think. So what is invented about math? A lot of times the notation is something that's invented that seems like it's foreign and strange, and it is. The notation was invented perhaps for a good reason, but it may look really obscure for someone. But if that notation is delivered to a student after they've identified whatever the pattern is, and then that notation just names that thing, rather than trying to teach the kid some new content through the notation, then that tends to work better. Then they don't feel like it's some new thing, some Greek that they have to learn. Rather, they already know what the thing is that they're doing, and now they have a way to describe it using notation that everyone else can understand as well. Does that make sense?
Mm-hmm. So fundamentally, math is about counting stuff. So we kind of, at the beginning, we started out and said, oh, you have 2 houses and I have 1, and so that's 1 to 2 or something.
Yeah, exactly. I mean, I would say in the beginning, math is about 2 things. It's about counting things and about measuring things. So if these are the basic things that we do when we're really small, we understand first that I am one person and you are another person. So we have the idea of 2 distinct things, and all of our counting is about realizing a stability among discrete objects. So 3 people, if another person comes in the room, it's kind of the same as if you have 3 apples and someone puts another apple on the table. So that idea of 3 or the idea of 4 is already an abstraction from our experiences, but it's an abstraction that all of us can make sense of. And measuring is the same way. It's the kind of thing of taking 2 things and trying to see which one is larger, and trying to figure out which one's larger, even if you can't pick one up and move it over and compare it to the other. What are you going to do to figure that out? So all of those things, I think, are stable in our realities. And all of the mathematics that we come up with, those mathematical ideas are abstractions from those 2 basic propensities that we have, all because we're trying to figure out our world.
Can you describe division by 0? How is that? How does that describe something natural in the world? Because I've heard people say, I don't believe in math because that doesn't make sense.
Okay, division by 0. Okay, you would pick something so difficult. I mean, yes. Realize that dividing by 0 was something that took a very long time for people to even realize that they could do. I mean, even just having a number that represents 0, not as holding a place value, but as its own thing, and how to operate with it. This is something that the mathematicians of India came up with first. Brahmagupta and his later counterpart Bhaskara came up with, but they didn't actually have it right at first either. And it wasn't something that you see in Europe until much later. So dividing by 0 is a weird thing to do. Even just operating with the 0 is a weird thing to do too. People had been dividing for years before that. So I'm saying this is a hard question. But
it must be helpful for something, or we wouldn't have it around. So in the context of it helps us describe our world, what does division by 0 help us describe in the world?
I would say it doesn't help us describe our world as much as it is an abstraction of something that we already are using to describe our world, which is division. So let's say we divide by a normal number. I'll give you an example. All right. When kids learn multiplication, they learn, let's say you have 3 tanks of fish, and there are 6 fish in each tank. And so they learn 3 groups of 6 is 18. So they count those groups of 6 3 times. It's repeated addition. Okay. That's what multiplication is. Division there are two different kinds of division that come out of this. Either I can give you 18 fish and there are 3 tanks and I want to know how many fish are in each tank, or I can give you 18 fish and I give you 6 fish in each tank. How many tanks do you need in order to exhaust the fish, right? So this sounds pedantic, but I'm getting at something here, okay? Those two different kinds of division problems, kids don't immediately see that those are the same thing. Okay, they think about those in different ways. One, you're given the total and the groups. The other, you're given the total and the number in each group, and you have to figure out the other thing instead. So think about dividing by 0. The first way, which in math education world we call partitive division, it doesn't really make a whole lot of sense. You have 18 fish, and you have 0 tanks to put them in. How many fish go in each tank? Well, I don't know how many fish go in each tank. 0? It doesn't even make any sense, right? This is where you say, I don't understand what dividing by 0 is. It doesn't give me anything. But the other one makes more sense. I have 18 fish, and I want to put 0 fish in each tank. Each tank can only hold 0 fish. How many tanks can I fill up before I exhaust the 18 fish that I started with? Well, really infinitely many tanks, right? I'm putting 0 in each tank. So it's an abstraction from a normal thing that we know how to do. If we want this to be coherent, the only possible answer for that is that I can have infinitely many tanks. So something divided by 0 has to be infinite. And that's what Bhaskara realized when he was the first person to really talk about this. It has to be infinite. There's no other way that it could be anything else.